Okay, this is the beginning of our chapter 4 notes. So you'll need to make a new table of contents for chapter 4. Chapter 4 is called Integrals. And today we are going to start section 4.1. It's called Antiderivatives. And indefinite integrals. So go ahead and update your table of contents, pause the video if you need a second. So we're going to start this next section, section 4.1, antiderivatives in indefinite integrals or integration. They mean the same thing. We're going to talk about that word in just a minute if it sounds unfamiliar. So we have this word antiderivatives, and it means exactly what it sounds like it means. It's the opposite of a derivative. So the inverse or opposite of the derivative is called an antiderivative. So what we're going to be doing in this chapter, and specifically in this section, is we're going to focus on doing our derivatives kind of backwards. So we're going to talk about one of the problems we run into and how we're going to incorporate that into our answers. So, for example, if we had a derivative, like if we already took the derivative, and f prime of x was equal to 3x squared, then we can kind of figure out that our original function, so f of x before we took the derivative, that would have been x cubed. Because if we take the derivative of x cubed, we bring the 3 down in front and subtract 1 from the exponent. But here's the problem. What if it was plus 10? When we take the derivative of 10, it goes away. So we wouldn't know if that 10 was there or not. But what if it was a different number? What if it was like minus 3? There's no way for us to know if it's 10 or minus 3. Or what if it was like plus 632? We don't know between the 3 of these. It could be literally any number on the end because our problem is that the derivative of a constant is 0. So when we're working backwards, we don't know if there is a number in the end, and then if there is, what that number is. Because there could have been not a number, or it could be like literally anything, positive, negative, huge, small. Like we have no idea. Later, we're going to talk about ways that we can figure it out. But for now, we kind of need a placeholder. So, since we have a problem that the derivative of a constant is 0, to write an antiderivative, so when we write this answer, when we're writing f of x, our original function, equals x cubed, and we don't know what's on the end, we have this notation plus c, plus our constant. So we're going to have that pretty much on the end of every answer. So this is your new best friend. C is your new BFF. You need to have it. If you don't have it, your answer is wrong. So like put a little star around it, highlight it, build a little house for your new BFF because he's going to be coming around a lot. This C is very, very important because it encompasses whatever number is on the end, and those can really change our original function. So we have to have something in its place. So plus C, plus C, plus C, plus C, plus C, plus C. Okay, very important. So we need to talk about what our notation is going to look like. Because when we took a derivative, one of the things how we wrote that we were going to take a derivative is if we said like d over dx of x cubed. means you're taking the derivative of x cubed, and that is equal to 3x squared. So now we need some math notation to write like that we need to do the antiderivative. Antiderivative, another word for them is indefinite integrals. Oops. So our new notation, so before we get into like the exact notation, we do have a new word. If you've never heard of this before, it is called integration. So like that's the opposite of like if we said differentiation. That was our derivative word. And then so this is our antiderivative word is integration. We're going to be integrating. Okay. Now you have some printouts, so that's why our paper for this chapter is green. So this is in green. So this is a printout. So take a minute to put that into your notebook. You should have them in the middle of your groups. This is what an indefinite integral looks like. We have this integral symbol that kind of looks like a squiggle, and we'll practice writing these. We have f of x is going to be our function. The name for that is an integrand. So it's like what you're integrating. And then what's going to be really important is we have this dx at the end. This is another thing. This is another friend along with c. So remember when we were like typing things into our calculator didn't know what our variable was. And in our calculator, we had to have comma x to let our calculator know that that was our variable. Well, when we're integrating, we have to indicate our variable. So this is what dx means. Dx means you're integrating x. You could integrate y, so you would have dy. You could integrate a, so you could have dA. Most often, we're going to have dx. That is part of our notation. Then what's going to happen is usually, like, we're not going to start with f prime. We're just going to have f. So in order to integrate f and go backwards, in order to notate like before, to take a derivative, we went from f to f prime. Now when we integrate, we're going to go from f, and to go backwards, it's going to become a capital F. So it's going to become capital letters. So this is our antiderivative, and then we have our BFF C. We built a house because we want him to be comfortable because he's our best friend. And that's called the constant of integration. It's the constant that goes on the end every time we integrate. Okay, so these are kind of all of our parts, all of the words that can come up. So with this in mind, we have, this is how it's said, is the antiderivative of f. And then this dx, we say with respect to x, is how we say that. Okay. So now we need our actual integration rule. So our basic integration rule, I guess it's just one rule, so we don't need that. Let's delete that. Okay. Our basic integration rule is another printout. You have a green thing that says antiderivatives, so go ahead and get that and attach this. So if we have f of x equals x to the n. To take a derivative, what we would do of if we had x to the n, we'd bring n in the front, drop it down, x, and we would subtract 1 from the exponent. Okay? So we need to do the opposite of that. So if our process was bringing this down, then subtracting 1, this is multiplying, this is subtracting, we're going to have to do the opposite of those in the opposite order. So what's going to happen is we're going to end up adding 1 to our exponent because that's the opposite of subtracting, and we're going to end up dividing. So because that's the opposite of multiplying. So this is kind of just opposite operations. So to get capital F, what's going to happen is you're going to have x to the n plus 1, so you're going to add 1, and then you can either write the division out front as a fraction, or you could literally write it like underneath. N plus 1 is going to go underneath. Now, it's a little bit different because these numbers are actually going to match. Okay, they're going to be the same when we integrate. So either one of these, and then of course we have our best friend C at the end. Okay. So this is just saying, like, if you took the derivative of capital F, you would get to lowercase f. So it's just denoting that relationship. Okay. So these are the steps. There are 2 steps, just like our power rule has 2 steps. You're going to add 1 to your current exponent. Then you're going to divide your coefficient. So if there's a number in front, you're going to divide that by the new exponent. So again, these new numbers that you're putting in are going to match. Okay. So let's look at some examples and see this rule in action. So our first example, we are going to integrate. So integrating, we're going to have this little squiggle. It's not going to look perfect at first. You're just going to do your best. The more you write it, the better it's going to be. Okay. So it just has to be, it can't be straight. It has to be some kind of squiggle. It needs to be curved. It's kind of like an elongated S. Okay. We're going to integrate x to the 4th dx. That's our problem. When we see this, that means we're integrating. So we're going to follow our rule. Our rule has 2 steps. First, we're going to add 1 to the current exponent. So this will be x. Our current exponent is 4. So we're going to add 1. Then we're going to divide by that exponent. So we're going to divide by whatever 4 plus 1 is. Now, 4 plus 1, you could do that in your head and skip it. Don't forget your BFF. He gets sad when you forget him. Plus C on every section of your answer. He can't just appear at the end, okay? You can't just call him at last minute and be like, hey, I need you. He has to be there the whole time. So there are a couple ways that you can simplify this. You can just add those numbers and you can write x to the 5th over 5 plus C. Or x over 5 is the same thing as writing 1/5 in the front, x to the 5th off to the side, plus C. So all 3 of these answers are equivalent. Either one of these that you want to write is fine. Just know that it can be written both ways because sometimes on multiple choice they write it both ways. Okay. So let's look at a couple more examples. Let's integrate 6x dx. So when we integrate, we add 1 to the exponent. So our exponent on x right now is 1. So we're going to add 1 to that exponent. We're going to have x squared. This x is just going to follow us along. It's just a constant, just like in derivatives. It just follows you along. And then we divide by whatever number we added. So we're going to divide by 2. BFF comes along plus C. Now, you can simplify this. So 6 divided by 2 is 3. So our final answer here would be 3x squared plus C. The thing about integrating is that you can always check by taking the derivative. If you want to check, just take the derivative of your answer. The derivative of 3x squared, multiply the 3 and 2, get 6. Subtract 1 from the exponent x. Derivative of c is 0. So it's just 6x. That's what we started with. We did this right. Okay. So let's see. Let's do the antiderivative of x to the negative 4 dx. So be careful here. This is a negative exponent. We are adding 1 to the exponent. So negative 4, oh, come on. There we go. Plus 1 is negative 3. Divide by negative 3 plus c. You can leave your answer like this, but we do have a negative exponent, so you can rewrite this answer. Since this is a negative exponent, this would move x to the bottom. 3 is already there, so that would just stay. So we'd have a 1 as a placeholder up top. We'd have 3x cubed in the bottom, and our 3 on the bottom was negative, so this is negative. Don't forget that negative. And then, of course, plus c follows us because we want him with us because he's our best friend. Okay. Then we have a couple of things in this one. So we're going to integrate x to the negative 4 minus 6x plus 8 dx. So I want you to take a second and see if you can do these. So it's just like taking a derivative that you just do one at a time, and then you have your final answer. So x to the negative 4th, we just integrated that. We know that we're going to have x to the negative 3 over negative 3. Negative 6x. We have a 1 exponent, so we have minus 6x squared over 2. Now what about 8? There is no x. If there is no x, remember that's basically like having x to the 0 power. So it's not like derivatives where a constant goes away. What happens if we don't have an x? 0 plus 1 is 1. So this gives us plus 8x to the first power, and then technically it's divided by 1. But dividing by 1, power of 1, you don't have to write those, so you can just go straight to 8x. And don't forget plus c. To simplify this, we do need to be able to simplify this. We already simplified this first term right here. So negative 1 over 3x cubed. Here we can have 6 divided by 2, so we have minus 3x squared. Here, this is just plus 8x, and then plus c. And that whole thing is our answer. Oh, there we go. So what about the integral? So work on your squiggles of x cubed plus 2 dx. Pause the video and try this one. The parentheses around the integral don't really mean anything. They're just saying that this whole group is being integrated. Sometimes you'll see the parentheses, sometimes you won't. So to integrate this, we add 1 to the exponent, x to the 4th over 4. And then 2 is just a number, so that becomes 2x. Do not forget, plus c. Now you can write this. This x over 4 can also be rewritten as 1/4 x to the 4th plus 2x plus c. Either one of these is fine, okay? But you have to be able to recognize both of them. Then we have one more example. The integral of x to the 1/2 dx. So we have our exponent, 1/2. You're going to add 1 to that exponent, 1/2 plus 1. Well, if you need to do some side work, 1/2 plus 1 would be 1/2 plus 2 over 2, which gives you 3 over 2. So you divide by that same number. Oops, put plus 1. Oh, come on. Try that again. Plus 1 plus c. So we have x to the 3 over 2 divided by 3 over 2 plus c. Now dividing by a fraction means keep, change, flip. So you would keep the top, change division to multiplication, and flip that fraction. So when we get our answer, it would, instead of 3/2, it would be 2/3. X to the 3/2 plus c. Okay. If you wanted to write this as a radical, this x to the 3/2. Numbers on the top are going to be your exponent, and then the number on the bottom is going to be your radical. So if it's a 2 on the bottom, it's just a square root, and then x cubed would be on the inside. This is basically an invisible 2, so bottom goes on the outside, top goes on the inside. So that's how you would rewrite that if you wanted to, but you can just leave your answer as 3/2 unless you're instructed to do otherwise. Then we want to look at a couple more things in this first section.